Okay, I think except the last row in the middle, we all have a copy. Okay, please, I need silence more than ever because we are not going to have the microphone. Now, let me summarize certain things that we have observed. Now, this is a very typical manufacturing environment. If your numbers would let, I would usually take you to a field trip and go to a factory and visit a factory and listen to people working there. Unfortunately, I couldn't find, well, I can find factories that will accept up to 100 students. Now, you are 170, and I don't know how to manage it, so that's the reason why we placed it with a video. Of course, don't worry, you're going to see a lot of factories before you graduate. And so you can ask, for example, your student club, whichever you are working with, to plan some trips to different factories. They would usually do that. Okay, now let's summarize certain observations. These are at the same time certain keywords that you need to know. So if in an exam, if you ask me what is quality control, I will not answer it as usual. Well, regardless whether it is what you want to learn or not, I'm not answering it anyhow. So quality control, you need to know what it means. So make to order, remember, in production planning, this is important. The customer is known, so we only manufacture to when we have the order. Now, in actuality, you're going to see that this is not the real case. This is how they claim, but actually this is not necessarily very true. Because certain parts, like metal sheets that we have seen in the first body part, they start with a metal sheet like this, and then they start to have holes, and then they give shape to that metal sheet. Now, all those operations, that metal sheet, you need to probably order 2 years in advance. Okay, so in other words, the customer is not there yet. But when it comes to the final assembly, of course, you want the customer to be there. You can see that because the colors and all the other details are set according to the customer desires. Now, this is important, and you're going to see the distinction between make to order and make to stock in your third year course, okay, which is called production planning, and in some other courses, you're going to see similar things. Quality control, any questions that you want to ask on production planning? Okay, quality control. Quality control is a very important concept, especially in these days. The things that makes certain products different than other similar ones is the way that they set the quality limits. For example, when you are buying an equipment, let's say a cellular phone, you have to make sure that it is going to work under different conditions. Okay? So you don't want to pay a little bit less, but have suspicion on the usage, if you can, of course. Okay, so these type of things are extremely important for industrial engineering. It has a large technical part associated with it. It is one of the original topics of industrial engineering, like process plans and so on. Quality control is a topic of industrial engineering since 1920s. And there are a large number of improvements, modifications, and so on in the old theory that is associated with quality control. So it will be a very interesting course. Now, in quality control, you always have the following dilemma. Should I inspect everything 100%, or should I do a sampling and do the inspection? Now, of course, if you are manufacturing planes, you are going to have 100% inspection, because we're talking about maybe 300 planes a year. Whereas if you are manufacturing a bicycle, where the number of bicycles that are manufactured in the world is probably around 100 millions. So probably you do some sampling. You don't actually control make a quality control operation on each of them, but you basically take a sample in a reasonable way, and you're going to learn how to do that partly in your statistics courses and in the quality control courses. And what is the meaning of being in standard, being under control, and so on, are those things that you're going to learn in quality control. Another thing that we have seen, any questions on quality control? I think it's straightforward. Most of the things here are very straightforward. The idea of stages of production. Okay? Now we can see that there are some stages of production which are followed, for example, body stage, and then paint shop, and then other things. Of course, we are only seeing part of the operations that are taking place in that company. Okay, you want me to answer? Can I ask you a question, please? Yes, you. Tell us a story that you have been reading in your phone so that we will all be happy as much as you are now. Please tell us what you were reading. No, I'm just, okay, so pointing like this it means that I'm going to get a lot of people. I was pointing at the guy at the back. You, yeah. No, the other one. Yeah. You had the phone and all your friends were looking at you. Okay, so what were you having in the phone so that let's hear that so that we will also feel the same comfort as you were feeling. At Instagram. So what was the picture? Picture of a car. Okay, so it means that it's related to the course. So you are pardoned. Okay? So you can go out of jail now. Okay, now, of course, this is something that I don't want because it distracts me as well. Because you have a lot of people looking at your phone. I know that there are other individuals who were dealing with the phone as well, because when I point it out, I can see a number of hands like this. So please behave, okay? Please. So let's go to the stages of production. Now you can see that in rice cooking, you also have stages of production. Okay? Now this is important when you are planning a production. It turns out that this is something which is important to follow. Now, who defined these stages? Now, these stages are defined according to the use with a lot of experience. Now, one of your friends asked about why did we have paint shop independent of the assembly line? So why did we have paint shop as another stage? And why it wasn't included in the assembly line? Because if we include that in the assembly line, things would move faster probably, rather than having it somewhere else. So any ideas on why the paint shop was not a part of the assembly line? So any? Yes? Paint needs to dry. So the operation is very long. It takes 10 hours. Another reason, yes?
It should be in a clean environment.
Okay, I think that's correct. It should be a clean environment. So we have two reasons, which are definitely the reasons that is not included. Yes?
In assembly line, all the operation is fixed, but in paint shop, there are different colors. For example, the seal or the...
Okay, that's partly correct, partly incorrect, because we don't know the operations that take place in the assembly line. I can assure you that it will be different if you have different requirements that are brought by customers. Each of them do have its own requirements. So the roof color is going to be another requirement. But I think the two reasons that we have seen here are the reasons why it is not included. I can tell you that in 1920s, when the first assembly line was established, painting was also a part of the assembly line. But throughout the years, because of the toxicity that is created by painting operation, and at the same time the length of that operation required that it should take place in another location. Moreover, the process which is used actually takes a number of them together and puts it for drying. So you don't dry it one by one, but you put it in a large oven so that they will be dried all together. So the batching of the items is also another reason why it is not part of it. Now, actually, it turns out that the person or people who are planning these type of operations are coming up with the definition of these stages. Now, in rice cooking, we know that we can divide into different stages, and probably we can obtain different definitions of stages if we divide it in an ad hoc way. But with experience, it turns out that there are certain ways of doing it. It turns out that this is something which is critical because we are dealing with a very technical issue, but the way that you see the operations, you group them, you may group them in different ways, and that will yield different requirements for production planning. So you're going to hopefully see the effects of those in that course. Okay, any questions? Okay, now integrated logistics center. Now this is basically a part which has less to do with the company, with manufacturing, because basically it is like a warehouse, and we already talked about that. Just-in-time ideas are very nice. This is how we want to operate. But if you recall that part of the talk that she was making about just-in-time, there were a lot of words like sufficiently large, close shortly, and so on, which turns out to be, which makes the planning of these type of operations extremely difficult. They are always talking about trade-offs. There are two trade-offs in a company like this. You can order all the parts 2 years ahead of time, but they are going to wait there. It means that you pay for it and they wait there. Versus if you order too late, then what will happen? You will have delays in your production, so that assembly line is going to stop. On the other hand, the money that you pay for transporting them is also an issue. If you order one by one, okay, it might cost you a lot. Whereas if you order in bulk, Tuzcuoğlu will bring it, and then it will be cheaper. Okay? So there are a number of issues that should be dealt in a more analytic way. Words are nice, but this is what you're going to learn in those courses, actually, in production planning and other courses. The ideas are there, but basically we materialize those ideas. Okay. Final assembly, the moving floor idea has evolved a lot. Anybody who proposed me to work on assembly lines in this classroom as your term paper topic? For example, a very good term paper topic would be history of assembly lines. Very nice, actually. You can find lots of papers about that. No, because I know you all did the same thing. OR applications in hospitals and OR applications in transportation, nice weather OR applications, clean air OR applications, and so on. Well, anyway, I will work on that as well. Okay, so this is actually a very interesting topic. So if you have time, you can Google it even, and you will find a lot of information. How the assembly line has evolved since early 1910s. Okay, now the last line is improvement. Okay, we are already familiar with improvement. And another thing that we learned is the teamwork effort. So people who does the actual job can bring in some proposals, then the engineers are going to examine whether those proposals are going to work or not. So the spark that I was talking about, if you recall, you need to have a spark. Spark is coming from the teamwork effort. So they are bringing in the spark, but only 4% of that spark is actually materializing. Okay, so it's a small percentage. Okay, questions? Okay, let's go to the next page. Now, there are two things that we should always remember. I think this is crucial to remember. One of them is, now we have seen a manufacturing environment. And although the environment is definitely a manufacturing environment, there are lots of things that has been done in a very similar way to a service environment, like a supermarket. For example, what happens if you are working in the production planning department of this company? What happens if you are working in the logistics center of this company? You are probably not even going to see the factory floor. Okay? So does this mean that you are working in the manufacturing sector? Well, of course, technically speaking, you might be working in the manufacturing sector, but what you are doing is not really manufacturing. You are organizing the services that are required for manufacturing. So this is important, basically, because when somebody asks you, hey, industrial engineer, what is your sector of operation? Okay? Your answer should not be manufacturing sector or service sector. You will say, always, if there is an organization which is complex enough, we can do a lot of work in that organization. Whether that organization is in this sector or in the other sector or in the last sector or in the first sector doesn't matter, because basically that's what we do. Moreover, working in Mini does not necessarily mean that you are doing a manufacturing job. Okay? Because there are many jobs in Mini which are not related to the manufacturing floor. So the type of duties you carry out determines your specialty, not the sector. Okay? You might be a very good supermarket person who might work at Mini doing the same thing, might work at Migros doing the same thing, or might work in another place at Kızılay doing exactly the same thing. Okay? This is very important to understand, because this is one of the things that you will consistently be asked. In Turkey, we have the understanding of relating a job, a profession, with a sector. Okay? Like, for example, if you are a service person, let's say a waiter, okay, serving, waiting tables and so on, you work in a restaurant sector. But when it comes to engineers, which has other types of background, we are probably a little bit above that. But believe me, the same thing is true for other engineers as well, most of the other engineers as well. Okay? So you are not related to any sector. Okay? Any questions on this? Always remember the layout that you have seen in the beginning. There were a number of rectangular blocks, and probably 2 of those rectangular blocks were related to manufacturing. The other blocks were related to service. Okay, questions? Okay, I think after this point, what we're going to do is we're going to go back to our nice network structures and define another problem in networks. So this time I'm going to use the board. So let's see how I will be able to do that. Any questions so far? Okay. Let me start, and then we will see whether we have enough light. I think they are coming on. Now, in the remaining time, we will see a network problem which is actually very much practical. And then next week, we will continue on doing this tomorrow, and then I will generalize the things that we have found in networks. Now, the problem that we are going to deal is the so-called assignment problem. Okay, can you read my handwriting? Okay. Now, what do we mean by an assignment problem? Let's say that we have n tasks. So think about the assembly line. You have n tasks in an assembly line. And then you have n workers that will perform those operations, those tasks. Okay, for example, if you are training, for example, a football team, you have 22 players. Actually, the number of tasks that are required is 11. You have a goalkeeper, you have the left hand, whatever, right hand, whatever, and so on. Each of them is a task, actually. And then you're going to assign people that you have in the team for those tasks. Particularly, what you have is, you have the following. You have to make sure that, in this case, I am assuming that I have equal number of workers and tasks. And we're going to do the extension tomorrow, which is very simple. Okay, so we have equal number of tasks and workers. So then what I will do is, I will write what the problem is. A worker, of course, can be assigned exactly one task, or let me write will be assigned, of course, not can, because basically we are not allowing the worker to do two things. And similarly, I can write the following. Each task will be assigned to a worker. So as all the trainers in football say that, well, if somebody is out for injury, we are not going to come up with 10 people and play. We are always going to have 11 people. So you are always going to have somebody assigned. Each task, each position will be assigned to somebody, to a worker. Now, what is important in this problem environment is simply the following. We have cost of performing a task is a function of worker. So, for example, if you have a star player, the star player will have very little cost regardless if she or he plays in the front or at the back. Doesn't matter, because the star is going to really help the team out. Whereas if you have a lemon player meaning that it's mediocre player, regardless where you put that player, the cost is going to be high. And that is similar thing goes true for workers. If you have a slow worker, regardless the task that you put, the time will be slow. However, that's the team that you have, and you have to assign that person a task as well. Okay, so of course you can see that our objective will be to minimize the total cost. Now, this cost might be time, not necessarily it's monetarily cost. It's a function. It can be time. It can be something else. But what we want is we want to minimize this. Any problems with the problem, assignment problem? Anything that you don't understand up to this point? Now, this problem seems to be a simple problem, actually. You can manage it. And there are various different environments which you can apply this idea. First of all, you can really have tasks and workers, okay? And that's how you're gonna do. And another thing is that you might have, for example, think about a certain organization. You have 11, 12 different jobs that you need to perform. And if you have 11 or 12 people that will do this, you have to make that assignment so that everybody is going to have a desk and work for it. Or you might have, for example, student tutors or student assistants who are going to assist you. If we have enough number of student assistants, how am I going to assign them to you? Okay? Now, what is the cost in this case? It might be whether we might have an index which is telling us whether this couple will be able to work or not together. So we might have some people who are very social, will be able to work with a lot of people, their cost will be low, whereas there might be some other type of people, regardless who they work with, will have a large index value. So, but my objective would be, I would like to minimize the total index value or the total cost of this assignment. So this is the problem that we are dealing. Now, I can show this problem using a network. Okay, and let me show it using a network. So here, I'm going to have, these are nodes, and I'm going to have n nodes. And let me say that these n nodes are tasks. And on the other side, I'm going to have another n nodes, but these are going to represent workers. Now, in this problem setting, I am assuming that each task can be performed by any of the workers. So this means that I have an arc that will connect this one with all the workers. Similarly, I have an arc that connects task 2 with every worker. Similarly, I have an arc connecting task n with every worker. And I will have some numbers written on these arcs. And what will be those numbers? The cost. So cost of worker 1 performing task 1. So this is going to be what it writes here. And similarly, I'm going to have other things written there. So the problem that I am going to do then will be defined in the following way. So I am going to select exactly one arc leaving any task node. So here I have n arcs leaving a task node, and I'm going to select only one of them. So I will do for every one of them. And similarly, what I will do is I can describe the same thing looking from this side as well. There are a number of arcs entering worker node 1. I am going to select one of them. But note that once you select a certain arc, then you won't be able to select that for another node. Am I right? For example, if you select this arc 2, 1, then I won't be able to use task 2 or worker 1 in any of the other assignments. Because then I simply close that. So this is actually a relatively simple problem. And let us see actually how we are going to deal with this type of a problem. Let me give an example. I think the best way to show it is an example. So this example will be actually a simple example, but I think we will be able to discuss that example and make my certain points clear. So here I will have 4 tasks and 4 workers. And the times that we have, or the cost, are given here. So I will have 39, 65, 69, 66, and 64, 84, 24, and 92, and 49, 50, 61, 31, and 45, 48, 55, and 23. So I have 4 jobs, 4 workers. Now, does it really matter whether I place workers here or jobs here? Doesn't matter. It is a completely symmetric problem. Okay. So after this point, I don't know what the real application is. I don't need to know this, actually. So if I learn how to solve this, and if I find the applications that will fit this structure, I will be able to solve them. So my role as engineer would be, if I can see a certain problem that I observe is fitting this structure, then I will be able to use this. As an engineer, you have to make sure that you know how to solve the problem, but also at the same time, you have to make sure that you can formulate the problem in this way so that you can solve it. So that you will see a certain problem described to you in a certain lousy way, and you have to understand that it's an assignment problem. Okay, now, okay, let's see some people who thinks they have solved it. Yes? No? Yes? Go ahead. No, no, no. Tell me the assignment. Yeah.
I just choose this one from the, for example, for first step. I choose this one.
Which is 39.
Yes.
For rows or columns? Rows. So this is your selection. Next one. 24. Next one. Next one. Which one? 48. Okay, how do you make sure that this is the optimal? You didn't use 23, which is the smallest number here in the tables. So you never know whether it is optimal or not. One more solution. Who claim, and I want you to claim that it's optimal. This is not the optimal one. Okay, yes. Speak louder. 50? Okay. Shh. I can't hear you. Yeah. 50, 23, and 24, and 39. Okay. And, well, when I look at here, I can see that there is a 48 here, which is a little bit less, and 49 here, which is a little bit less. So it might be a good solution, but I don't know. I'm not sure whether it's optimal or not. Okay, now let's work on this problem. Let's use our mind to work on this problem. We're going to solve this problem optimally tomorrow and on Friday. But let's work on this. Let's try to get some structural properties as we talked before. Okay? Now, for example, let's start with the first one. Now, what I can do is, one thing that I can do is the following. I'm going to take the minimum of each row. Okay? And hope that it is going to give me a feasible assignment. Now, that's what you were trying to do. Minimum of the first row, 39. Minimum of the second row, 24. Minimum of the third row, 31. Minimum of the fourth row is 23. Unfortunately, it doesn't yield a feasible solution. Because basically, it means that I'm using this worker twice for two different jobs. Now, another thing that I can do is, of course, I can do the same thing for the columns, because it doesn't matter. The problem is symmetric. So select the minimum of the first column. Select the minimum of the second column. Select the minimum of the third column. Select the minimum of the fourth column. No, it doesn't work, again. But basically, this is again infeasible. Why? Because whether this is a job that I have here or something else, I'm using it twice. But however, what can I say about the optimal solution? If these numbers, one of those, row minimum, sum of row minimum, so let me write this. So so this is important, and I am going to call it lower bound. You remember the lower bound that we already learned what it was. So the lower bound that I have here would be, if any one of these were feasible, I know that it will be the optimal. What do I mean by feasible? Feasible means that I am finding an assignment which is applicable. So I am finding an assignment where a worker is assigned exactly one task, and each task is assigned to a worker. Okay? So everybody is happy. Everybody has a task or a job to fulfill. Okay? So what is a lower bound then? I'm going to sum the minimum of each row. And what is this value? So this is simply 39 plus 24 plus 31 plus 23. Somebody please add that up for me. 197. This is 70, 37, 137. Yes, that's what you said. Okay. Now, of course, I can do the same thing for the columns. So I can add minimums of each column.
The minimum of the each row is wrong. It is 117.
So this is 117. You're right. Thank you. Okay. Minimum of each column. Is it feasible? Unfortunately, it's not feasible. But I know that any solution that I can find which is feasible is going to be larger than that number. So let's look at the minimum of each column. Add that up. So this is going to be 39 plus 48 plus 24 plus 23. So I have most of them the same, but instead of 31, I have 48 here. So it means that this is 17 larger, and this is going to be 134. So I have two lower bounds. When I look at the columns, it says that it cannot be worse than the worst, the best solution that you can get is 134. This one says that the best solution that you get is 117. So which one is true, do you think? Which statement is correct? The first one says that the best solution that you can get is not less than 117. This says that the best solution that you can find is not less than 134. What can you say about these two statements? First of all, are they correct? They are correct. So these are correct statements. This is a lower bound. This is another lower bound. So if I am going to use one of those, which one am I going to use? First one or the second one? First one. Okay, but be courageous. Second one. Okay, of course second one. Because basically it's a lower bound which is higher. And it is going to give me a closer value to the value that I am looking for. Both of them are correct statements. So this one says that you cannot find a solution which is less than 117. This one says that you cannot find a solution less than 134. So this is going to be a better one for me. So my lower bound that I'm going to select for this problem will be the maximum of those two numbers, which is 117, 134, will be 134. So if you give me a solution, I'm going to compare it with 134 and make some remarks. Okay, this is very nice actually. We are starting to learn in the way that industrial engineers think about certain problems. This is how you build up knowledge of this type of structures. It's not only for this one. We have seen lower bound in another problem environment. This is another one. And you will probably have a third one coming in the exam. Okay? So this is the way that actually I think. Okay. Let's look at another property. So this is actually number one property. Number two. Now, what happens if I take the first row and subtract 39 from every element in the first row? So subtract 39 from all elements of the first row. So what does this mean? It means that, let's say that this was worker 1 doing task 1, 2, 3, and 4. So I am replacing worker 1 with a faster worker 1, keeping the differences between the times that the worker spends for different tasks the same way. But I am saying that the first job will be performed in 0, the second one will be performed in, well, 26 time units, the third one 30, and the fourth one will be 27. Now, do you think that what we are trying to find is changing if I change the numbers this way? I didn't change anything, actually. Relatively speaking, they are all staying in the same way. As long as I am adding up these numbers in the objective function, the only thing that will change will be the total cost that I'm going to come up at the end. The total cost that I'm going to come up at the end with this structure is going to be whatever it comes plus 39. Now, I can do the same trick for each row, and believe me, I can do the same trick for each column as well. Now, what are the uses of these zeros? So let me do it to each row. Let me do that to each row. This is going to be 40, and I'm going to have a 0 here. I'm going to have a 0 here, and numbers here, a 0 here, and numbers here. What are these zeros going to represent then? Well, relatively speaking, it shows me where the assignment should be, if I can do the assignment, of course. And if I see 0, can I have anything less than 0? Because all the numbers are going to be positive. Can I have anything less than 0? No. So these are my candidate assignments. By doing this, I simplified the problem. There were lots of numbers there. I simplified the problem. It turns out that this is something that you can use for solving a number of other things, including systems of linear equations as well. Okay, so this is actually something that we're going to use. So subtracting a certain number, adding a certain number to each row or column is not going to change the value, the overall value. Okay? So let's keep that in mind because we are going to use that tomorrow. Of course, total cost will change by 39. So, of course, total cost will change by 39. And similarly for the others. Okay. Now, of course, when I do this subtraction, if I obtain zeros in a feasible way, then it means that I found the optimal solution. Okay? Now, what I will do is, and that's what we're going to do tomorrow, we're going to apply these type of operations in a systematic way to obtain zeros in different columns and in different rows, and then finally obtain the assignment. It's called the Hungarian algorithm. Why is it called the Hungarian algorithm? Because Ottomans used to be very good with Hungarians. You know, we were very good friends. Have you ever been to Hungary? Okay, did you take a tour? They will always talk about the brutality of Ottoman Empire. Now, this is a Hungarian algorithm which tries to zero everything. It has nothing to do with what's going on in these days. Okay? Zeros everything, and we're going to see that tomorrow and on Friday. Any questions?